I have a velocity versus time graph with the following parameters. Do you see the parameters that are there? First, I'd like a sketch of a position versus time graph. And then, if you'll remember things we talked about last week, you should be able to numerically tell me the acceleration experienced by the object and the displacement experienced by the object. And if you don't remember all the things that we talked about spread over all of last week, I have some information here to help you. And I will throw down one thing. I encourage you to know or look up what the area of a trapezoid is. I hope by now you have, but if you haven't, I'm still willing to help. Just not as much as maybe you'd like. So I'm going to call on two people, one to tell me the acceleration, one to tell me the displacement. I will come by and take a look at your graphs. Just a quick sketch. Don't make too much of it. So when you're looking at a sketch of a position graph, this is what it should look like. It was moving away from the origin the whole time. The velocity was always positive. And it started with a high velocity, ended with a less steep velocity. So I expect my position graph to be getting closer and closer to zero for the slope. And that's what this is. Now, what's that? I can't hear you. Acceleration is? You're close. Anytime a numerical answer is asked, a unit has to be provided. This time it would be meters per second squared. Okay, because it's meters per second was in the numerator and seconds in the denominator. And this is close, but it's a vector quantity. This is a negative acceleration, right? The slope is negative, so I expect the answer to also include the vector portion of the answer. So you could say towards the origin if you'd like, but negative will suffice. Any questions about what I was expecting there? Anybody need me to work this out? All right, so let's see who is next. Who's sitting at 6? Nobody, so it falls to 7.
Okay, so displacement, I think I calculated this correctly.
Okay.
Is it negative 640 meters?
I don't believe so. And the reason I'm not trying to throw away your number or anything, but the area here looks like it's going to be a positive area.
Okay, I was confused with the
It's okay.
meters per second, so I thought like maybe my answer was wrong before.
Well, let's work it out. First, you are finding an area. Can everybody confirm for me that we are looking at the area bounded by these two blue lines? They represent the bases of the trapezoid. If we look at this as a trapezoid, they're base 1 and base 2 because the base of the trapezoid are the parallel lines. And these are the parallel lines. So 1/2 base 1, which is 100, plus base 2, which is 20, times the height. The height is the perpendicular distance between the two parallel lines, which in this case has to be that line, which is 16 seconds long. Any questions where I came up with those? The units inside the parentheses are meters per second, and the units in the other parentheses are seconds. So these are gonna, when we multiply together, meters per seconds will cancel with seconds. We'll get meters as our unit here. So this will be 120, half of 120 is 60, 60 times 16, 960, right? So 960 meters. This is the displacement. This is the symbol we will use for displacement, is delta x. And just like for acceleration, delta x and acceleration are both vector quantities. So I put the little delta above the top, I put the little line above the top to indicate that they are a vector quantity. There's more here that I need you to understand. Delta is a symbol you already know, right? You've got that from Algebra 1, so you're familiar with the fact that delta means change in. So we could translate it as change in x. And x is the symbol that we use for position. And position is a vector quantity. Now this part, I believe you should also know that delta x could be written in this fashion. Final position minus initial position. So whether I write it as a delta or I write it as the actual final minus initial, they have the same meaning. And if you need to, you can always replace delta for x minus x naught. These are all vector quantities. And one thing that I don't think you guys will understand right away is that the direction of delta x doesn't necessarily have to be the direction of either of these two. It's the direction of the change. That's important. Now, I want to change this. I want to see if you can work outside the box a little bit, but so far, have we seen how this works? Okay, so I'm going to change it not much, just enough. Oops, I want to take all that away. I just want to take this away. So I'm going to pull all the numbers out of this. All the numbers gone. And then I'm going to take the same line I'll try to at least. Maybe not. There we go. I'm just going to slide it down a little ways so that now it starts at 60, but ends at negative 20. Now, if you are paying very close attention, you'll know I didn't change one thing. Which thing did I not change? The acceleration, right? Same line, same slope. But I did change the starting velocity. This is still going to be 16 seconds for our time. Can you tell me the displacement of the vehicle? Many of you are going ahead and still using the trapezoid equation to figure out the displacement, even though this doesn't look like a traditional trapezoid. But that's okay. It's a non-Euclidean trapezoid. You guys have been kind of stuck in Euclid's math, but there are other trapezoids and other kinds of math out there. Euclid's math wouldn't allow a trapezoid to have an occlusion in the middle, a place where the lines cross. But non-Euclidean geometry would allow you to have an occlusion in the middle. I want you to imagine, and I asked this in first period, and nobody knew what I was talking about. How many of you know what a sunshade is for like a car? All right, so there's like two types out there, right? The accordion ones and the ones that you kind of fold up. If you take this trapezoid and fold it, right, the first step in folding up one of those shades, it's still a trapezoid. Okay, the only difference is that part of my area is positive and part of my area is negative. But we can still use the trapezoid formula to figure out the displacement. Consider the car, its motion looks like this now, right? The position versus time graph, because it went forwards for some time and then went backwards for some time. But ultimately, I can still say 1/2 base 1, which is 60, plus base 2, which is negative 20, times t, which is 16, should give us our displacement. So if I run the numbers on this, 320 meters. That's the displacement of the vehicle. Now, that's the difference between here and here, right? That's the displacement. That's where the car is at the end of the interval compared to the beginning. A different question is, how far did the car go? Can you find that answer out? Because that's a different question. The car went forwards and then went backwards. So finding out how far the car went might require knowing when this happened. So try. I can't give much time for this, but I can give a little time for this. Try. At your disposal, you have the model for this function. The model y equals mx plus b works for this function, right? It's a straight line, right? In fact, we talked about this last week. V equals AT plus V naught. That's the function. And you know information about the function. You know V equals negative 5t plus 60. right? This is the model. From this model, you could use it to determine time, right? We want to find out the time when the velocity is 0. So plug in 0 for the velocity and solve for t, and you'll get 12 seconds. That is when the velocity is 0. Once I know that that's 12 seconds, well, then I have an area here, and I have an area here. I can find the two separate areas. First area, 360 meters. 1/2 base times height. The second area is going to be negative 40 meters. 1/2 base times height. Any questions? Because if there's no questions, I'm going to assume that I'm speaking to a room that knows what I just did. We're good to go? Now, this has to have corroborating evidence, and it does. 360 plus negative 40 gives me 320, right? That was our original displacement. If I add these two areas together, it tells me the car went forwards 360 meters. That's here, right? That's the furthest the car went from the origin. Forwards 360 meters. Then went backwards 40 meters. That's why the displacement's 320. But the total distance traveled by the car, 400, right? 360 plus 40, 400 meters is the total distance traveled by the car. Any questions about this? It will make sense when I'm doing it. Well, I hope it makes sense when you're doing it at home. Because this is the kind of stuff I would expect to see on your test. And these are just straightforward kinematics questions. They're not really physics yet. In fact, I want to take this and make you consider something. I'm going to erase everything again if you're good for us to move forwards. So I'm going to get rid of all the numbers that are here. If this is truly a generic velocity versus time graph, then our velocity starts at some initial velocity v0 and ends at some final velocity v, and does so over a time interval t. Okay? We said that the slope is the acceleration. By definition, slope is the change in the horizontal change in the vertical divided by the change in the horizontal, which would be v minus v0 over t. All right, that's how we would calculate slope. And this isn't a surprise, but if you solve this for v, the final velocity, you get v equals at plus v0. You get the function that we would expect. It's a linear function. That's how y equals mx plus b works. All good? Any question about that? Well, consider displacement. We know it's the area of the function, and we just, I think, clearly showed that using the numbers, regardless of whether they're positive or negative, nets you the appropriate displacement. Well, that's just this. Now, I'm bringing this to your attention because we just took a generic linear graph, applied the information we know about velocity and acceleration and area and slope, and generated two relationships that, apart from the graph, could be used in any situation regarding a constant acceleration system. Right? This only applies to systems in which the acceleration is constant. If the acceleration is not constant, this wouldn't be true and this wouldn't be true. This is only true because the acceleration is constant. I've emphasized this 3 times because you have a set of homework questions that are about non-constant acceleration. You can't apply any of what I'm about to say to that. These only work because the for the velocity graph is a line. It's linear. But with that, it generates 5 motion variables and 2 relationships that each have 4 motion variables in them. And if we look, this relationship has everything in it but displacement. And this relationship has everything in it except for acceleration. These two relationships can be used to solve every single motion equation problem, all the kinematics problems, as long as the acceleration is constant. There's a couple of caveats. One of the caveats, and this is an important one, is that this only works for one object at a time, right? Our graph is always about one object, so this works for one object. It only works for one acceleration at a time. So any problem involving multiple accelerations, you might have to do this more than once. And any object involving more than one object, you might have to set up more than one set of motion variables, one for each object. But this will tell you what the object does for some time interval. It'll give you information. And if you look closely, excuse me, both of these relationships have only 4 motion variables in them, which means in any problem that you have to use kinematics, you're going to have to be given 3 pieces of information in order to solve for it, because your equations all have 4 in them. So as long as you have 3, you should be okay. Now, if I give you something that has 3 pieces of information in it, one of the things I do want to point out is these are more helpful under certain circumstances. So let's say I give you that the car starts at 60 meters per second and goes to negative 20 meters per second and does so in 16 seconds. Well, that was nice and contrite because it worked out perfectly for us in a manner that gave us one relationship that we could use to figure out displacement and one relationship that we could use to figure out acceleration. And it worked out just fine. But what if instead I didn't give the final velocity and I gave something like the displacement? I say I went 100 meters. Well, suddenly I wouldn't be able to use just one of these to solve the answer. I'd probably have to use both. I'd probably have to figure something out with both of them. But you guys are shrewd individuals, and you probably remember your math pretest. If you have 2 relationships that share common variables, you can manipulate them to create new relationships. Let me give you an example. Let's say I want to create a new relationship, but one that, say, doesn't have final velocity in it. Well, that would be easy, right? I can eliminate final velocity between these 2 relationships. I'd solve one for final velocity and plug it into the other. Since this is already solved for final velocity, which is kind of why I brought it up, I can take everything that's here and plug it into final velocity right there. If I do this, I'm going to create a new relationship that will have the 4 motion variables in it, but not final velocity. So let's try. Now here's where I have to do my substitution. It's AT plus V naught. There. Now, that looks okay, but it's always best if you can try and make your expression as simple as possible. So I'm going to do some distribution and stuff. First, I'm going to realize that inside the parentheses, this is actually AT plus 2 V naught. That's the first thing I'm going to notice. The next thing I'm going to do is I'm going to distribute, say, the 1/2. Is that okay with you guys? So I distribute the 1/2. I get 1/2 AT plus V naught. All right, 1/2 times 2 cancels out to 1, so that's why the 2 disappeared. And now I'll distribute the T. Now I've created a new relationship. You'll notice it has 4 motion variables in it and has everything except for the final velocity. So I'm going to go put it over here in my stack, and I'm actually going to put it next to the variable final velocity. I'm trying to organize us a little bit. So I'm putting the equation that's missing a variable next to the missing variable to remind us that there's always 5. Now, I have a couple reasons to do this one, but you see that you could probably figure out the other 2. Or you could just search and find Galileo's motion equations. That's what these are called. Galileo's motion equations. It's a set of 5 relationships that relate the 5 motion variables together. They can be used to solve all motion equation problems that involve constant acceleration. But do you notice right away that this one is quadratic? Remember at the beginning of the year when we talked about curved graphs, you guys tended to jump to exponentials. But no, all of our position graphs, right? Position is here, have been quadratic. That's the curve because it's based on a quadratic function. All right, that's it for today.